Alright, so this is C4. Learning outcomes. Recall the simple properties of groups 1, 7 and 0. Explain how observed simple properties of groups 1, 7 and 0, 0 meaning it can also be group 8 or group 18, depend on the outer shell of electrons of the atoms and predict properties from given trends down the groups. Recall the general properties of transition metals and their compounds and exemplify these by reference to a small number of transition metals. Predict possible reactions and probable reactivity of elements from their positions in the periodic table. Explain how the reactivity of metals with water or dilute acids is related to the tendency of the metal to form its positive ion. Deduce an order of reactivity of metals based on experimental results. Alright, so if we have a look at this slide here, so we know that in group 1, that means that there is 1 electron in the outer shell. Group 2 means that there are 2 electrons in the outer shell, for example, and so on. So when one valence electron, valence means in the outer shell, when one valence electron leaves during a chemical reaction, why does that happen? Well, it happens because it wants to achieve a stable outer shell. And so when that electron is lost, the number of protons will be greater than the number of electrons. So therefore, the charge is +1. Why does the atomic size of the alkali metals increase? Now, as you increase the number of protons, you increase the number of electrons. When we say going down the group, I mean starting from hydrogen, going to helium, going to lithium. So when I say going down the periodic table, I mean as the proton number increases, and for atoms, the number of electrons is equal to the number of protons to have an overall of neutral charge. So as you increase the number of protons, you also increase the number of electrons for a neutral atom. Now, as you increase the number of electrons in the atom, you also increase repulsion, but because there are more protons in the nucleus, you also increase the attraction between the protons and the electrons. However, overall, you will still end up with electrons repelling each other in the atom. So the general trend is that the atomic size of the alkali metal atom increases. Let's carry on reading. The single valence electron becomes further away from the nucleus. Now, as you increase the number of electrons, you increase the number of protons, the electrons get further away from the nucleus, and as it gets further away from the nucleus, the attraction between the nucleus and the electron gets weaker. So that's why that's partly the reason why it becomes further away from the nucleus. The outer electron is screened by more inner shells containing electrons. Now, as you increase the number of electrons and you increase the number of protons, the inner shells become more attracted to the nucleus. But because the inner shells are attracted towards the nucleus, the lonely outer electron gets further away. So that's what it means when it says the outer electron is screened by more inner shells containing electrons. The effective nuclear charge felt by the single valence electron decreases when going down the group. Okay, so let's have a look at the phosphorus atom. Now, phosphorus atom is in group 5, and that means that there are 5 electrons in the outer shell. And because the atomic number is 15, the electronic configuration becomes 2, because you always fill the inner shells first, and you can only fit in 2. So 15 minus 2 is 13. And then the second shell can fit in 8. So now 13 minus 8 equals 5. So 2 electrons in the first shell, 8 electrons in the second shell, and 5 electrons in the outer shell. Now let's just focus on the inner shells. So because they are full, and so the total full shells are 2, and the total number of electrons in those 2 shells is 2 plus 8. So if you're just focusing on the full shells and the nucleus, you end up with 15 protons minus brackets 2 plus 8 close brackets. So you end up with 15 protons in the nucleus minus 10 full electrons, meaning that now that should say 5 protons, not 5 electrons. So therefore there are 5 protons in excess. So because now you have 5 protons in excess, the effective charge is plus 5, and this only includes the full shell and the nucleus. And what that means is that if you include the full outer shells of the atom and the nucleus, the effective charge is plus 5, and you end up with minus 5 in the outer shell. So the shielding effect describes the decrease in attraction between an electron and the nucleus in any atom with more than one electron shell. The more electron shells there are, the greater the shielding effect experienced by the outermost electrons. Now if you look at this one here, now if you're just focusing on the hydrogen atom, because the hydrogen atom is the most simplest atom, you've only got 1 proton and 1 electron. So the elements closer to hydrogen, the net force on the electron is as large as the electric attraction between the nucleus and the electrons. However, as you go down the periodic table, when there are more electrons involved, each electron feels also the repulsion of other electrons and the attraction between the nucleus. So if you look at the diagram, you've got attraction between the nucleus and the electrons, but also you have repulsion between other electrons. So this causes the net electrostatic force on electrons in outer shells to be significantly small in magnitude. Therefore, these electrons are not as strongly bound as electrons closer to the nucleus. This is called the shielding effect. And this shielding effect explains why outer electrons are more easily removed from the atom. The nucleus can pull the valence shell in tighter when the attraction is strong. Now what that means is that if you have a full electron, the attraction is strong. However, it is less tight when you don't have a full shell. So therefore it is less tight when the attraction is weakened. The more shielding that occurs, the further the valence shell can spread out. As a result, the atoms will be larger. So remember that group 1 metals mean the electrons in the outer shell is only 1. Okay, let's carry on reading. Right, let's look at the trends of the melting points. So if you look at the trends, the melting point decreases and the boiling point decreases. The melting point and boiling points decrease going down group 1 because the atoms get larger. Melting points are lower than for typical transition metals because alkali metals only have 1 electron in their outer shell. Not much heat energy is needed for this electron to be lost. So as you can see the trend, the melting point goes down. Now this is because the outer electron gets further away from the nucleus. As the electron gets further away from the nucleus, it doesn't need that much energy for the outer electron to be lost. Okay, so the ionic radius is the distance from the nucleus to the outermost electrons in an ion, but the atomic nucleus is the distance from the nucleus to the normal valence electrons. That is spelled incorrectly. That should be VALENCE. Okay, so the atomic radius versus the ionic radius. Now let's have a look at why the sodium ion's radius is a lot smaller than the sodium's atomic radius. That is because the sodium ion would have lost the electron. When that electron is lost, there is no more outer electron, and so when there is no more outer electron, the radius becomes smaller because now you end up with a full electron in this outer shell. Similarly for the magnesium, as the magnesium's outer electron gets lost, because now there is no outer electrons, the radius becomes smaller, so the ion becomes smaller. However, if you look at group 7 elements, the fluorine, because the fluorine atom has gained an electron, now there are more electrons than the protons. Now the reason why it gets larger is because the number of electrons have increased. That increases the repulsion between other electrons. So all the extra other electrons increase in size because of the repulsion. Similarly for chlorine, because now there are more electrons than protons, the repulsion increases. That increases the size of the atom. Right, so let's look at the trend for group 1. So the atomic radius increases as you go down the group because the outer electron is attracted less. Why? Because there are more electrons in the outer shell, more electrons in the inner shells. Outer electron further away because of shielding. The ionic radius also increases as you go down group 1. Outer electron is attracted less because more electrons in the inner shells, outer electron further away because of shielding. Melting point. Now the melting point decreases as you go down because the electrons are now further away from the nucleus. And so because the outer electron is further away from the nucleus, the outer electron will be weaker. There'll be a weak attraction between the nucleus and the outer electron. Now let's have a look at this trend here. So the trend, if we just focusing on the alkali metals, the atomic radii will increase. So if you're starting from lithium, going to sodium, potassium, rubidium, and cesium, the atomic radii will increase because you increase the number of protons and you increase the number of electrons. And as you increase the number of electrons, they repel each other. That increases the size of the atom. Also, if you focus on if you look at the noble gases as well, as you increase the atomic number, the radius also increases. But you can see that it's a lot more. The radius is a lot more smaller than the alkali metals. Now, the reason for this is because it is very stable, and the more stable the atom, the smaller the radii, because it's very stable. Unlike the alkali metals, where there is only one electron in the outer shell, it is further away from the nucleus, is a lot larger. But because the noble gases are generally less reactive than the alkali metals, the size of the atom is a lot smaller. Okay, so the trends in the alkali metals. The atomic radius increases as you go down the group. Ionization energy decreases down the group. Now, ionization energy means the energy required to remove one electron from the atom. So it's very low ionization energies. Again, that's because there is only one electron in the outer shell. It is further away from the nucleus, so you don't need that much energy to remove it. So that's why it is very reactive. If you look at the second tick, very reactive, not found uncombined in nature. It reacts with non-metals to form salts. These are ionic compounds. Compounds generally soluble in water, found in seawater, for example, sodium chloride. Melting point decreases down a group. We explained why. Because the electron is further away from the nucleus, so therefore you need less heat energy. All very low melting points for metals. And the density increases down the column, except potassium. In general, the increase in mass is greater than the increase in volume. Right, so now we've done the group 1, let's look at group 7. So yeah, if we look at this, lithium, sodium, potassium, as you go down the group, the outer electrons gets further away. So if you're just focusing on the last shell, where there is the outer electron, remember that the metallic radius increase, and so therefore the attraction between the nucleus and the last electron, the last shell electron, will decrease. It gets weaker because it's further away. So therefore, if you remove the last shell electron, that gets easier, and also the metallic characteristics also increase because of the delocalized electrons. Okay, so let's have a look at group 7. Now let's have a look at the order of reactivity of the halogens, group 7. So in this case, as you go down the group, it becomes less reactive, because if you look at fluorine, which is higher up group 7, you only need 1 electron to fill in the 7 electrons in the outer shell. But as the atom gets larger and larger, the 7 electrons gets more attracted towards the nucleus. It is the complete opposite of the group 1 elements, because for group 1, the single electron is much further away from the nucleus. But for group 7, because there are 7 electrons in the outer shell and it is almost completely full, those 7 electrons are pulled in towards the nucleus. So the reactivity will decrease down group 7. So for example, fluorine is more reactive than chlorine, and bromine is more reactive than astatine. And as you go down group 7, the size increases, again because the number of electrons increase and the number of protons increase. If we look at the melting points and boiling points, they both increase. Why is that? Again, this is the opposite to group 1. So in group 1, the melting point and boiling point decrease because the single electron is further away from the nucleus, and so therefore it is easily lost. You don't need that much energy to remove that single electron, the single outer electron from the nucleus. But because group 7, the electrons get closer towards the nucleus as you go down the group, the melting point and boiling point will increase. The halogen molecules increase in size down the group. This leads to a greater van der Waals forces between molecules. Now, van der Waals forces just means intermolecular forces. So van der Waals is a type of intermolecular force, increasing the energy needed to separate the molecules and therefore higher melting and boiling points. So that is another reason why, as group 7 elements go down the group, the melting point and boiling points increase. Okay, so let's have a look at some of the key points. Now, group 17 is the same as group 7, it's the same. Now, why is it 17? Well, because the group 17 includes the transition metals. Group 7 does not include the transition metals. So, as you move down group 7 or 17, there is a decrease in reactivity, opposite to group 1. It increases in the atomic radius, the size of the atom. It increases in the number of filled electron shells. There's a decrease in the power of the halogen to attract an electron to form a negative ion. And as you go down group 7, there's an increase in melting and boiling points, and the color of the element will get darker. And let's look at the trends for the noble gases. So if you look at the chart above, the boiling point will increase as you go down the noble gases. So the melting point and boiling point increases down the group. They are all gases at room temperature. They have low boiling points. The density increases down the column, and in general the increase in mass is greater than the increase in volume. So let's have a look at this table. The atomic mass increases down the periodic table. The boiling point increases down the table, and the melting point increases down the table. The density increases. Now let's have a look at the ionization energy. The ionization energy decreases. Well, that's because even though it's because this is again quite similar to other elements, because the shells get further away from the nucleus, the energy needed to remove an electron from one of the noble gas atoms will decrease because the electrons are further away from the nucleus, so therefore the ionization energy is a lot less as you go down the group, so it decreases. The atomic radius increases as you go down the noble gases. Alright, let's have a look at the properties of transition metals. So the physical properties, the transition elements share some physical properties with all metals. They conduct electricity in the solid and liquid states. They're shiny when freshly cut. Some properties of transition elements are different from those of the metals in group 1. Compared to other metals, most transition metals have higher melting points, higher densities, greater strength, greater hardness. Now, these are typical properties. However, some transition metals may not show one or more of them. For example, mercury melts at minus 39 degrees. So it is a liquid at room temperature. The general trend for a decrease in reactivity from left to right across the periodic table, there are some exceptions, such as zinc, which is more reactive than expected. So in the transition metal section, there's a decrease in reactivity. Another exception is iron, which does react quite readily with air and water, causing rust. Also, transition metals can form paramagnetic compounds. The colors of transition metal compounds are due to two types of electronic transitions. Transition metals are conductors of electricity, possess high density and high melting and boiling points. So these are some of the colors for the transition metals in aqueous solution. Alright, so if you look at this chart here, so the iron 2 plus would be green. Iron 2 plus is green. Iron 3 plus is more yellowy brown. Copper 2 plus is blue. Now, if you look at potassium chromate, now one of the oxygen atoms is 2 minus because oxygen is in group 6, so therefore it would form an ion of 2 minus, and because there's 4 of them, that makes it 8 minus. Now, here you can see that there's an overall charge of 2 minus, so 8 minus and 6 minus, you need a 6 plus. So the chromium is a 6 plus, that makes it yellowy orange. Manganese 2 plus is pink. Cobalt 2 plus is pink. Nickel 2 plus is green. Now again, look at the potassium manganate. One oxygen is 2 minus, so if you have 4 of them, that makes it 8 minus. But you have an overall charge of 2 minus, so you need a manganese 6 plus. So it should be more purple, more pink, purplish pink. And then potassium dichromate. So oxygen, one of the oxygens is 2 minus, there's 7 of them, so that makes it 14 minus. But 14 minus, you need an overall charge of 2 minus. So 14 minus 2 is 12, and then 12 divided by 2 is 6. So you want to look at chromium 6 plus, which is orange. Is that the same as the... Okay. So if we look at the trends for the melting points in the transition metals, there is no, here it says on the slide, here it says it does show no regular pattern other than nearly all being high, which is typical of metals. if we look at this graph, yeah, there is no pattern, so it is going up, down, up a bit and then down. So there are two distinct regions here and here. So manganese is so the peak could be said for vanadium and chromium, and then you got a minimum for manganese, and then it goes back up to iron, cobalt, nickel, and then it goes back down to copper and zinc. So it doesn't show a regular pattern. So the melting point, it goes up, down, and up again, and then down. And then the densities, the general trend for the transition metals is that it goes up apart from zinc. So the similarities are more noticeable than differences, although there are still some broad patterns. They are all dense heavy, which is what we expect of metals. If you look at the metallic radius, if you start from scandium, it goes down all the way up to nickel, and then it goes up again. So after nickel, it goes back up. So the metallic radius, the general trend is that it decreases, and then after nickel, this is only for the first row of the transition metals, it goes up after nickel. And also the general trend is that the ionization energies increase slowly across the row, as do densities. So the densities does increase slowly. If we go back to this one, so the densities increase slowly. So does the electrical and thermal conductivities. But there is no trend for the melting points. There is no regular pattern. You can say that it goes up to chromium, goes down to manganese, goes back up again, and then goes down, leading to copper and zinc, where they are the lowest melting points. And for catalysts, how are transition metals good in making catalysts? A catalyst is a substance which speeds up the rate of a chemical reaction by providing an alternative pathway that will lower the activation energy. Transition metals make good catalysts as they change oxidation states by gaining or losing electrons. This means they can transfer electrons to speed up reactions. Now let's have a look at the reactivity series. We're looking at C4.1e. Explain how the reactivity of metals with water or dilute acids is related to the tendency of the metal to form its positive ion. So if you look at the reactivity series, the most reactive is potassium, then it's sodium, lithium, barium, strontium, calcium, magnesium, aluminium, manganese, zinc, and so on, going all the way down to platinum. Alright, so if we relate this to the periodic table, so if we look at where it says on the far right, where it says number 1, so potassium is the most reactive, and it is in group 1. So that's this one here. So group 1, potassium is the most reactive. When we talk about potassium, because potassium is quite common, rubidium, cesium, and francium are more likely to be radioactive. And so that's why we have potassium first. So potassium, where is this 1 on the far right of this slide? So potassium is the most reactive, and then after that it is sodium. So it's going, instead of going down the periodic table, it's going up. When we say it's going up, I mean it gets less. The atomic number gets less. So the potassium is the most reactive, then it is sodium, then it is lithium, and then it goes into group 2, where it's barium, and then strontium, calcium, magnesium, and then it goes into aluminium. Aluminium is in group 3 or 13, and then after aluminium it goes into manganese, zinc, chromium, iron, and cadmium, these are all in the transition elements. So these are all in the transition elements. Okay, so the stability of the metal's electron configuration as atoms and as ions determine their reactivity series. Potassium has a single outer shell electron because it's in group 1. Potassium is in group 1. And it is easily lost because it's in the outer shell. So therefore it is more reactive. And because it wants to obtain a full outer shell. So potassium has a single outer shell electron to lose in order for it to attain a stable electronic configuration. That's why it's very reactive. The precious metals which exist in the D block cannot form structures which are much more stable than their elemental state with the loss of just a few electrons. Now, when it says D block, these are the transition metals. So the precious metals which exist in the transition metals part of the periodic table cannot form structures which are much more stable than their elemental states with the loss of just a few electrons. Metals which loses only one electron are more reactive, so in this case it's group 1, and then after group 1 it is group 2, which require the loss of more than one electron. Metals with a greater total number of electrons tend to be more reactive as their outermost electrons, the ones which will be lost, exist further from the positive nucleus and therefore they are held less strongly.